Hello, everyone. Welcome to TechAPale. Okay, so picture this. You've got two computers connected with a cable. That's the physical layer, layer one. But all that gives you is a raw, messy stream of ones and zeros. So how do these machines turn what's basically electrical noise into an actual, meaningful conversation? Well, that's the big puzzle we're going to solve today.
So what's the big deal with layer one? Well, it's just raw, completely unstructured data. I want you to imagine trying to read a book that has no spaces, no punctuation, no sentences, just one giant, endless string of letters. It would be total chaos, right? The computer on the other end has no clue where one piece of information stops and the next one starts. It's basically unusable.
And this is where our hero of the day comes in, the data link layer, or as we call it, layer 2. Its entire job is to step in, take that chaotic mess from layer 1, and bring some order to it. Think of it as the friendly neighborhood traffic cop for devices that are plugged into the same local network. So how does it create all this order? It does it through a process called framing. And this is, without a doubt, its most important job. The data link layer grabs that endless river of bits and chops it up into nice, neat, manageable chunks that we call frames. It's just like taking that giant string of letters and finally organizing it into proper sentences that we can actually read. Now, a frame has a very specific structure. As you can see right here, layer 2 takes a packet of data from the layer above it and wraps it up, or encapsulates it. It sticks a header on the front and a trailer on the back. That original packet of data just becomes the payload in the middle. It's literally like putting a letter into an envelope before you drop it in the mail. You know, that postal service analogy is the absolute best way to understand what layer 2 does. Think of it as your local mail carrier. Their job isn't to get a letter from London to Sydney. Nope. Their only job is to get that letter from one post office to the very next stop on its journey. It's all about that one local hop. And this brings us to one of the most important concepts in all of networking, the difference between MAC addresses and IP addresses. An IP address, which is a layer 3 thing, is like the final destination address on that letter. It stays the same for the whole trip. But a MAC address? That's the address for the immediate next stop. It's a physical address that's permanently burned into your device's network card, and it changes at every single router your data passes through. So here's the key takeaway. As your data zips across the internet, the IP packet inside, that's our letter, stays exactly the same from start to finish. But the layer 2 frame, the envelope, gets ripped open and a brand new one is created at every single router along the way. Each new envelope gets a new to and from MAC address, guiding it to the very next device. We call this whole process re-encapsulation. Okay, so this leads to a pretty logical question, right? If your computer wants to send something to another computer on your Wi-Fi, it knows that computer's IP address. But to actually build the frame, it needs its physical MAC address. So, how in the world does it find it? Well, the answer is a clever little protocol called the Address Resolution Protocol, or ARP for short. The easiest way to think about ARP is as the local network's phone book. Its one and only job is to look up an IP address and find the matching physical MAC address. And the whole process is really simple. As you can see here, PCA basically just shouts out to everyone on the local network, "Hey, who here has this IP address?" Every other device on the network hears the shout, but they all ignore it, except for PCB. PCB, who actually owns that IP, replies directly back to PCA and says, "That's me," and "Hey, here's my MAC address." And just like that, they can start talking. Okay, so we know layer 2 handles addressing and framing, but it's not done yet. To make sure that local delivery is smooth and reliable, it also has to enforce a couple of really important rules of the road. And these two rules are error control and flow control. To put it simply, error control is all about checking to see if the data got damaged along the way. And flow control is about making sure a fast sender doesn't send information way too quickly for a slow receiver to handle. For error control, layer 2 uses that trailer we talked about earlier. Inside it, there's a special value called a frame check sequence, or FCS. It's basically a checksum. Before the frame is sent, the sender does a quick calculation on the data and puts the result in the FCS. When the frame arrives, the receiver does the exact same calculation. If the numbers match, great, the data's good. If they don't, the frame is considered corrupt and it just gets thrown away. Now, this is important. Layer 2 detects errors, but it doesn't correct them. Now, flow control is just as critical. Imagine your brand new, super fast laptop trying to send a big document to an old, slow printer. Without flow control, your laptop would just flood the printer with data, overwhelming its memory, and a bunch of that data would get lost.
Flow control makes sure the sender waits for the receiver to say, okay, I'm ready for more, preventing that from happening.
All right, that's enough theory. How does all this stuff actually work in the real world? Well, the truth is, you're interacting with Layer 2 devices and protocols literally every single day.
The most common Layer 2 device you'll find is a network switch. When you plug your computer into the wall at the office, you're probably plugging into a switch. A switch is like a smart traffic director. It pays attention to all the traffic and builds a little table that maps the MAC address of every device to the specific physical port it's plugged into.
And here's what that table looks like. So when a frame comes in for the MAC address ending in 2D21, the switch doesn't have to shout it out to everybody. It just looks at its table, sees that device is on port FAS 0/1, and sends the frame only down that specific cable. This intelligent forwarding is what makes our network so fast and efficient today.
And of course, all this behavior is governed by rules, which we call protocols. The two you're going to see all the time are Ethernet, which is the king of wired networks, and 802.11, which you probably just know as Wi-Fi. At the end of the day, they both do the same fundamental job of framing and local addressing, just over different types of media.
And just as a final cool fact, networking pros often split Layer 2 into two smaller sublayers. The top half is the LLC, which basically talks to Layer 3. The bottom half is the MAC sublayer, and that's where all the physical addressing stuff we've been talking about actually happens. You don't have to memorize this, but it's good to know it's there.
So let's zoom out for a second. We've gone through a lot of details, but why does any of this really matter? Why is Layer 2 so absolutely critical to how the internet works? Let's recap the 4 main jobs of the data link layer. First, it's our local delivery expert, making sure data gets from one hop to the next. Second, it's the packaging department, creating those frames. Third, it's the local phone book, using MAC addresses to find devices. And finally, it's the quality inspector, checking for errors to make sure our data arrives safely.
And that brings us to one last big question. Layer 2 is fantastic at getting data from one device to the very next one, but its vision is limited. It has no idea what exists beyond its own local neighborhood. So if Layer 2 is so good at local delivery, why do we even need Layer 3, the network layer? Well, that's a question for our next explainer. If this explainer finally made that whole MAC versus IP address thing click for you, do us a favor and hit that like button. Make sure you subscribe for more explainers that break down complex tech. And if you have any questions at all, drop them in the comments below. We read every single one. Thanks for watching.